Awesome. Hey, good afternoon everyone. I think wala pa ka muna sawa for the whole day. Share my screen. Yan. Can you guys see? Wala lang ka PowerPoint. So, by the way, please try to check and read our syllabus sa mga subjects natin. It is posted sa Neo LMS, no? Ang aton nga course syllabus para may idea kung sa ating course outline. But maybe some of the topics will not be covered, or maybe hindi siya matackle, no? Because of the time. Okay, so our first topic for today, for this afternoon, for Physics 2, we'll focus on thermodynamics. Okay, so I'm sure you already have an idea from the introduction of thermodynamics during our Physics 1. So we have the first law of thermodynamics, no? And the second law of thermodynamics. Before that, we will first explore the temperature, the heat, no? And then we will go to the next module, which is the second law of thermodynamics. And so one of the principal branches of physics and engineering, okay, is thermodynamics. Okay, so which is the study and application of thermal energy, or what we call internal energy of systems. Okay, so one of the central concepts of thermodynamics is, of course, temperature, which we begin to explore in the next section. So since childhood, you have been developing a working knowledge of thermal energy and temperature. Diba? So we have a sense of touch, syempre. So you know to be cautious with hot foods, hot stoves, or to store perishable foods in cool or cold compartments. So you also know how to control the temperature inside home and car, and how to protect yourself from wind chill and heat stroke. Okay, so examples of how thermodynamics figures into everyday engineering and sciences are countless. So automobile engineers are concerned with the heating of a car engine, such as during a NASCAR race. And of course, no, during this time, di ba? Meron kita ginatawag na climate change. So, iba na. Di ba? Iba na yung temperature sa environment natin. So, food engineers naman are concerned both with proper heating of foods, such as pizzas being microwaved, and with proper cooling of foods, such as TV dinners or TV diners being quickly frozen at processing plant. Then geologists are concerned also with the transfer of thermal energy in an El Nino event. El Nino. And in the gradual warming of ice expanses in the Arctic and Antarctic, so due to global warming. And agricultural engineers naman are concerned with the weather conditions, which determines whether the agriculture of a country thrives or vanishes. But hindi natin siya ma-predict, di ba? We cannot predict, but we can forecast. Yan, sa mga weather forecaster natin. So medical engineers are concerned with how a patient's temperature might distinguish between a benign viral infection and a cancerous growth. Di ba? So mabalaan mo ang isa katao kung may infection siya, kung ginahilagnat siya. Ginahilagnat. Yan. So the starting point in our discussion of thermodynamics is the concept of temperature and how it is measured. Okay. So first, we have the temperature. So what is temperature? So temperature is one of the 7 SI-based quantities. Okay, so physicists measure temperature on the Kelvin scale. So take note in SI units. So we have Kelvin scale, which is marked in units called kelvins. Although the temperature of a body apparently has no upper limit, it does have a lower limit. Okay, so this limiting lower temperature is taken as the zero of the Kelvin temperature scale, or what we call the absolute zero, or that is about 290 kelvins or 290 K as we write it. Yeah. So you can check here in the figure on the left, which has a wide range of temperatures. Excuse me, may naga-knock lang. Wala sir, nagpababaw siya. Feeling ko lang. Hindi na mapusin na. Okay, so we have here the range of of temperatures. There is a scale natin. Okay, so this is the universe just after beginning. So 10⁻39. This is in degree Kelvin. The highest laboratory temperature is 10 to 8. Center of the sun, it is in between, around 10 to 2 raised to 7. Then surface of the sun, ito yung mga recorded temperature nila. And the universe today, 10 raised to 0, of course. Boiling helium, okay, and so on. So when the universe began 13.7 billion years ago, so its temperature was about 1039 Kelvin, or at least 10 raised to 39. So as the universe expanded, it cooled, no? And it has now reached an average temperature of about 3 Kelvin. So we on Earth are a little warmer because, syempre, we live it in near star. Without our sun, we too would be at around 3 Kelvin, or maybe we could not exist. Pero may ara sa buong technology, no? China, they are planning to create an artificial sun. I'm not sure if you're aware with that. Try to research or try to search that if you're curious about their project. But what will be the consequences if there will be no day, if there will be no night? Okay. Yeah. So the zeroth law of thermodynamics. So the properties of many bodies change as we alter their temperature. Perhaps by moving them from a refrigerator to a warm oven. So to give a few examples, so as their temperature increases, what will happen to the volume? Of course, the volume of a liquid increases. And a metal rod grows a little longer, and the electrical resistance of a wire increases. So as does the pressure exerted by a confined gas. So we can use any one of these properties as the basis of instrument that will help us pin down the concept of temperature. So we have here thermoscope, natawag natin na thermoscope. This instrument is not actual, not a thermometer. Okay, so hindi siya yung actual temperature gauge, but it shows how cool or how hot a certain area is with the use of this instrument. Yan. So for example, we have here in figure A, ito, we put a thermoscope which we shall call body T. Ayan. into intimate contact with another body. Let's say body A. Ito. So the entire system is confined within a thick wall insulated box. Dito. Ito yung insulator natin. The numbers displayed by the thermoscope roll by until eventually they come to rest. So let us say the reading is 137.04 and no further change takes place. So in fact, we suppose that that every measurable property of the body, this one, and the body A has assumed a stable. So meaning there's no changes in both bodies. Then we can say that the two bodies are in thermal equilibrium, meaning equal silang dalawa. Okay? So even though the displayed readings for body T have not been calibrated, so we conclude that bodies T and A must be at the same or unknown temperature. But supposed to be, we next put the body T into intimate contact with body B in the next figure and find that two bodies become two thermal equilibrium at the same reading of the thermoscope. Then the bodies T and B must be at the same, still unknown actual temperature, but we have readings here. It is 137.04. So if we now put bodies A and B into intimate contact, like this one, so are they immediately in thermal equilibrium with each other? Yan yung tanong. So the experimental fact shown in the figure is summed up in the zeroth law of thermodynamics. That is, if bodies A and B are in thermal equilibrium with a third body T, then A and B are in thermal equilibrium with each other. Kung naging thermal equilibrium sila dito sa A and T, T and D, then A and B would be in thermal equilibrium with each other. Ayan. So in less formal language, the message of the zeroth law is everybody has a property of temperature. Okay? Everybody has a property called temperature. When two bodies are in thermal equilibrium, then their temperatures are equal. And of course, vice versa. So we can now make our thermoscope, the third body T, into a thermometer, which is confident that its readings will have physical meaning, which is 137.04. And all we have to do is calibrate it. Okay, so how we calibrate it? By using the exact equipment or exact measurement of the equipment. Okay. So we use the zeroth law constantly in the laboratory. If we want to know whether the liquids in two beakers are at the same temperature, so syempre measure natin siya each with a thermometer. So may ara ka sa beaker 1 mo, may ara ka thermometer, then beaker 2 may ara ka naman sa thermometer. So we don't need to bring the two liquids into intimate contact and observe whether they are or not in thermal equilibrium. So no need to ibutan mo sila sa isa ka beaker. Yan. So the zeroth law, which has been called a logical afterthought, came to light only in 1930s, long after the first and second laws of thermodynamics have been discovered and numbered. Okay, so because the concept of temperature is fundamental to those two laws, the law that establishes temperature as a valid concept should have the lowest number. Hence, we have the zeroth law of thermodynamics. And so next section, we have measuring temperature. So here, we first define and measure temperature on Kelvin scale. Then we calibrate a thermoscope so as to make a thermometer. Diba? So, nag-assign kita di kaginaw para makalibrate natin as a thermometer. So we have what we call the triple point of water, okay, or the T sub 3. So to set up a temperature scale, we pick some reproducible thermal phenomenon and quite arbitrarily assign a certain Kelvin temperature to its environment. So that is, if we select a standard fixed point and give it a standard fixed point temperature. So we could, for example, select a freezing point. Diba? Ano itong freezing point? Can someone identify what is the freezing point of water and boiling point of water? Yara? Ano itong freezing point sa water? Any idea? Wala? How about boiling point? Boiling point of water. Yara? Wala? 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 Assignment yun na ha. That will be your assignment. So in liquid water, solid ice and water vapor or gaseous water can coexist in thermal equilibrium at only one set of values of pressure and temperature. So it depends on the pressure and of course the temperature of the water or the liquid. So we have here the figure shows a triple point cell in which dito. So this is called the triple point of water, can be achieved in the laboratory. So by international agreement, So the triple point of water has been assigned a value of 273.16 Kelvin. So this is the standard fixed point temperature for the calibration of thermometers. Okay, that is the triple point temperature. So we have here our equation number 1, T sub 3 for the triple point temperature, in which the 3 here, subscript 3, means the triple point. So this agreement also sets the size of the Kelvin as 1/273.16 of the difference between the triple point temperature of water and absolute zero. So note that we don't use a degree mark in reporting Kelvin temperatures. So it is 300 K or 300 Kelvin, not 300 degrees Kelvin. Okay? So sometimes we make mistakes when pronouncing that parehas na lang sila sa degrees Celsius. So magkaiba gali sa degree sa Kelvin. So when you say Kelvin, Kelvin lang gid, wala na sang degree Kelvin. Okay? So the usual SI prefix applies. Okay, so thus 0.0035 K or Kelvin is 3.5 millikelvin. Yan, pwede na siya. So there will be no distinction in nomenclature is between Kelvin temperature and temperature differences. So we can write the boiling point of sulfur is 717.8 Kelvin. And the temperature of this water bath was raised by 8.5 Kelvin. So wala na sang 8.5 degree Kelvin. Yan. So yan yung tama. Okay. Next, we have the constant volume gas thermometer. So the constant or the standard thermometer against which all other thermometers are calibrated is based on the pressure of gas in a fixed volume. So we have here the figure shows such a constant volume gas thermometer. So it consists of a gas-filled bulb. So gas-filled bulb connected by a tube to a mercury manometer. So dito siya. Ito. So by raising and lowering reservoir of R, ito yung reservoir natin. So the mercury level in the arm or in the left arm dito of the U tube can always be brought to zero of the scale. So this is to keep the gas volume constant. Variations in the gas volume can affect temperature measurements. So para maging constant siya sa dito sa zero natin. Yan. So the temperature of any body in thermal contact with the bulb is then defined to be the temperature is equal to the constant, which is zero, or it depends kung ano yung liquid. So constant times the pressure. Okay? So the pressure here is exerted by the gas. And C here is the constant. Yan. For the equation, the pressure is equal to the atmospheric pressure multiplied by minus by the density of the mercury in the manometer multiplied by the gravity multiplied by the height, or this is the difference between the mercury levels in the two arms of the tube dito. Yan. Yung H mo, height mo. Yung difference niya. Yan. So the minus sign is used because pressure is measured above the level at which the pressure is the atmospheric pressure. Kaya nagsasubtract tayo. Okay. So if we next put the bulb in a triple point cell or triple point of water, then the temperature now is T sub 3 is equal to Cp sub 3, in which yung P sub 3 natin is the gas pressure now. So eliminating the constant between the equations 2 and 4, then we can have temperature as 273.16 Kelvin multiplied by the pressure divided by the atmosphere or the gas pressure. Okay, so divided by the pressure divided by the gas pressure. So we still have a problem with this thermometer. So if you use it to measure, say, the boiling point of water, we find that different gases in the bulb give slightly different results. However, as we use smaller and smaller amounts of gas to fill the bulb, then the readings converge nicely to a single temperature, no matter what gas we use. So it depends. Helium balay na, hydrogen, oxygen. So depende. Okay. So here we have the recipe or the equation for measuring the temperature with gas thermometer. So that is 273.16 Kelvin multiplied by the limit of gas, the limit of the pressure divided by absolute divided by the gas pressure as gas approaches to zero. Okay, so we have the limits. So the recipe instructs us to measure an unknown temperature as follows. So first, we fill the thermometer bulb with an arbitrary amount of any gas. So for example, nitrogen, and measure the P3 or using the triple point cell. Okay, so titingnan natin yung gas pressure. And then the P now, or the gas pressure at the temperature, is being measured. So to keep the gas volume the same, we need to calculate the ratio between the gas pressure divided by the triple point cell. Okay, so then repeat both measurements with a smaller amount of gas in the bulb, and again calculate this ratio. So kumbaga ano siya, isa-isa siya. Okay, so continuing this way using smaller and smaller and smaller until you can extrapolate to the ratio P over P sub 3, in which you would find if there were approximately no gas on the bulb. So ganyan ka tedious yung grabe ka complicated mag-measure. Okay? So the temperature is called the ideal gas temperature. Ito yung equation natin for ideal gas temperature. So take note na lang. Okay. Next, we have the Celsius and Fahrenheit scales. So far, we have discussed only Kelvin scale. So we used in basic scientific work in nearly all countries of the world. So the Celsius scale, formerly called the centigrade scale, is the scale of choice for popular and commercial use and much scientific use. So Celsius temperatures are measured in degrees. Okay, so dito tayo may degrees Celsius and degrees Fahrenheit, but in Kelvin, just Kelvin lang. Yan. However, the zero of the Celsius scale is shifted to a more convenient value than absolute zero. Okay, so if T sub 0 represents the Celsius temperature and T Kelvin temperature, then the temperature in Celsius is equal to 273.15 degrees. So ito yung equivalent niya. Okay? So ito yung equivalent niya. So in expressing temperature on Celsius scale, the degree symbol is commonly used. Okay? Thus, we write 20 degrees Celsius for a Celsius reading, but 293.15 Kelvin for a Kelvin reading. And so the Fahrenheit scale naman used in the United States employ a smaller degree than the Celsius scale and a different zero of temperature. So I know you already know this one, the conversion, di ba sa physics 1. This was introduced to you, conversion of temperatures. We have Celsius, Fahrenheit, Rankine, and Kelvin. Yan. So the same as this one. Okay, so 0 degrees Celsius is equivalent to 32 degrees Fahrenheit. Then if you need to convert that one, then you use the 9/5 multiplied by the temperature in degrees Celsius, then you add 32 degrees. Yan. Okay, so next we have thermal expansion. So you can often loosen tight metal jar lid by holding it under a stream of hot water. Yan. So ito yung technique, no? Isa sa mga technique para ma-open yung, let's say, palaman ng tinapay na nasa bote. Diba? So hindi mo ma-open. So yung isang technique dyan is pwede mo siyang pwede mo siya bubuan, gamay lang, or hinihinay lang, patuluan mo siya sa hot water sa gilid. Then, automatically, amat-amat na siya mag-expand ang glass mismo sa jar. Okay? And then, mag-open na siya yun. Ma-loosen. Yan, ma-loosen na siya. Okay? Isa sa mga technique. Okay, so that is because of, ayan, hot water adds energy to their atoms. Ayan. Then we have such thermal expansion of materials with an increase in temperature must be anticipated in many common situations. Ito, when a bridge is subject to large seasonal changes in temperature, for example, so sections of the bridge are separated by expansion slats so that the sections have room to expand on hot days without the bridge buckling. Okay? When a dental cavity naman is filled, then the filling material must have the same thermal expansion properties as the surrounding tooth. Otherwise, consuming cold ice cream and then hot coffee would be very painful. So, tawag siya ng sensitive teeth. So, when the Concorde aircraft, was built, so the design had to allow for the thermal expansion of the fuselage. So this was during supersonic flight because of frictional heating by passing air. So may mga rin sila. So mga applications in terms of thermal expansion. So the thermal expansion properties of some materials can be put to common use. So we have thermometers and thermostats may be based on the differences in expansion between the components of bimetal strip. Ito. Okay. So familiar liquid in glass thermometers are based on the fact that liquids such as mercury and alcohol expand to a different or greater extent than their glass containers. So, yan yung sagot. Bakit mercury yung nasa loob ng thermometer? Yan. Okay, so we have the linear expansion. Okay, so review na lang sa inyo. I think this was discussed sa previous physics 1. So if the temperature of metal rod of length L is raised by an amount of change of temperature, then its length is found to increase by an amount of the change in length is equal to the L multiplied by the constant, which is the coefficient of linear expansion. Okay, so it depends on the material. Okay, so we have ice at 0 degrees Celsius. So yung expansion niya is 51. Lead 29, aluminum 23, brass 19, and so on. Ito. Then multiplied by the change in temperature. In change in temperature dito, it would be the final temperature minus the initial temperature. Yan yung change of temperature dito. The coefficient alpha has the unit per degree or per Kelvin. So ito. Or pwede man 10 raised to negative 6 per degree Celsius. Yan. So note that the unit degree Celsius there could be replaced with unit Kelvin. So depende. So, pwede siya ma-convert. No? So this is in terms of degree Celsius. Pwede mo siya ma-convert to Fahrenheit or Kelvin. Okay. Next, we have the volume expansion. So the same formula, but in case of alpha, we use the beta here. So beta here is the coefficient of volume expansion naman, multiplied by the volume and the change in temperature. Yan. Okay, so of course, this will also depend on the temperature of a solid or liquid. Okay, wherein nag-increase siya by the amount of change in temperature. The most common liquid water, which is water, does not behave like other liquids. So about 4 degrees Celsius, water expands as the temperature rises. So that, as we would expect. So between 0 and about 4 degrees Celsius, however, water contracts with increasing temperature. Thus, at about 4 degrees Celsius, the density of water passes through a maximum. So at all other temperatures, the density of water is less than this maximum value. Okay, so this behavior naman of water is the reason lakes freezes from top down rather than the bottom up. Okay, so this is the reason. So as water on the surface is cooled from, say, 10 degrees Celsius toward the freezing point, it becomes denser or heavier than the lower water and sinks to the bottom. Below 4 degrees Celsius, however, further cooling makes the water then and the surface less dense or lighter than the lower water. So it stays on the surface until it freezes. So that's why baliktaran. Okay? So top down yung pag-freeze sa mga lakes. Okay? Okay, so we have here a sample problem. Okay, so we have here a sample problem. On a hot day in Las Vegas, an oil trapper loaded 37,000 liters of diesel fuel. So then he encountered cold weather on the way to Payson, Utah, where the temperature was 23 Kelvin, lower than in Las Vegas, and where he delivered his entire load. So how many liters did he deliver? So the coefficient of volume expansion for diesel fuel is 9.5 times 10 raised to negative 4 per degree Celsius. And the coefficient of linear expansion for his steel trap is 11 times 10 raised to negative 6 degrees Celsius. So take note that the givens here are in degrees Celsius. So you need to convert this one, your temperature here from Kelvin to degrees Celsius, or use the Kelvin in all instead. Okay. So to calculate this one, ito, but I'm afraid they do not, hindi nila kinonvert dito. Ba't kaya hindi nila kinonvert? So this is the change in volume. Okay, so change in volume is equal to, okay, so it doesn't matter, no? So change in temperature. Okay, it doesn't matter sa change in temperature. So unit degree Celsius could be replaced with unit Kelvin. Okay. So that's why hindi na nila kinonvert this one. So that is 37,000 liters multiplied by the constant one, that is 9.5 times 10 raised to negative 4 per degree Celsius multiplied by the change in temperature. So that is 0 minus 23, or that is 23 or negative 23.0 Kelvin. And that is equal to negative 808 liters. Okay, so therefore, the amount delivered was, that is the original volume plus the change in volume. So original volume is 37 liters or 37,000 liters minus the change in volume because of the temperature. Okay, so that is now the volume of the diesel fuel na i-deliver is just 36,190 liters and not 37,000 liters. Okay, so note that the thermal expansion of steel tank has nothing to do with the problem. So question, who paid for the missing diesel fuel? Yan ang tanong. So sana punta yung yung diesel fuel na nawala. So sino nagbayad nun? So of course, it is included here. But because of the temperature, obviously, nag-evaporate siya. Di ba? Evaporate siya because of the temperature. So obviously, there will be a change in volume. Okay? Kasama na siya dito. Di ba? Kasama na siya dyan. So, pagdating doon sa dindelivera niya, instead of 37, ito lang yung ano niya. Ito lang yung na-deliver niya. Okay? So, not actually, no, 37 imogin load. Ang magmamantid to is 37 because of changes in temperature. Yan. So, meron tayong linear expansion dito. Okay, so we calculate the coefficient of volume expansion of the diesel fuel. But of course, it will depend, no, kung ano yung mo ginakarga. Kung water ba na, salt water, fuel, basi mantika malang na iya. So again, it will be same computation but different results. Okay. Next section, temperature and heat. Yan. So if you take a can of cola from the refrigerator and leave it on the kitchen table, its temperature will rise rapidly at first, but then more slowly until the temperature of the cola equals that of the room temperature, wherein the two now are in thermal equilibrium. Okay? So room temperature ang cola, tapos ara siya sa room man mismo. Okay? So in the same way, the temperature of a cup of hot coffee sitting on the table will fall until it also reaches room temperature. So in generalizing this situation, we describe the cola or the coffee as a system with temperature T sub S. Okay? And the relevant parts of the kitchen as the environment with the temperature T sub E of that system. So our observation is that if T sub S is not equal to T sub E, then of course the T sub S will change. Wherein T sub E can also change some until the two temperatures are equal and thus thermal equilibrium reached. Okay, so such a change in temperature is due to a change in thermal energy of the system because of the transfer of energy between the two systems, the system and the system's environment. So you can recall that thermal energy is an internal energy that consists of kinetic and potential energies associated with the random motion of the atoms, molecules, and other microscopic bodies within an object. Then transfer energy is called heat and it symbolizes Q. So heat is positive when energy is transferred to a system's thermal energy from its environment. So let's say, or we say that heat is absorbed by the system. How about heat is negative? So heat is negative when energy is transferred from a system thermal energy to its environment. So we can say that heat is released or lost by the system. Okay, you can imagine that sa sa refrigerator. Okay, so positive heat bala or negative heat. And so this transfer of energy is shown in the figure below. Ito. The situation of figure A, in which the system temperature is greater than the environment temperature. So energy is transferred from the system to the environment. So as Q will be negative. Heat here is negative. In figure B naman, in which the system is equal to the environment. So therefore, there is no transfer. So therefore, ang heat natin dito is 0. So heat here is neither released nor absorbed. For the figure C naman, in which the temperature of a system is less than the temperature of the environment. So the transfer here is to the system from the environment. So meaning, the heat here is positive. So it gains energy as heat dito. And so we are led then to this definition of heat. So heat is the energy transferred between a system and its environment because of a temperature difference that exists between them. And so recall the energy that can also be transferred between a system and its environment as work, diba? So via force acting on a system. So heat and work, unlike temperature, pressure and volume are not intrinsic properties of a system. They have meaning only as they describe the transfer of energy into or out of a system. So it's just the same as a $600 transfer has meaning if it describes the transfer to or from an account, not what is in the account. Because the account holds money, not a transfer. So here it is, proper to say, let's say during the last 3 minutes, 15 joules of heat was transferred to the system from its environment. Or during the last minute, 12 joules of work was done on the system by its environment. So it's meaningless to say this system contains 450 joules of heat. Iba. Diba? Or this system contains 385 joules of work. Iba rin. So walang meaning. So before scientists realized that heat is transferred energy, heat was measured in terms of its ability to raise the temperature of water. Thus, we have what we call the calorie. Okay, so which was defined as the amount of heat that would raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. So in British system, the corresponding unit of heat was BTU, or what we call the British thermal unit. That is defined as the amount of heat that would raise the temperature of 1 pound of water from 63 Fahrenheit or 63 degrees Fahrenheit to 64 degrees Fahrenheit. So in 1948, scientific community decided that since heat or like work is transferred energy, the SI unit for heat should be the one we use for energy, namely the joule. Okay, so that is for the SI unit for heat. We have joule. So the calorie is now defined to be 4.1868 joules exactly. So take note of this constant with no reference to the heating of water. So the calorie used in nutrition, sometimes called the calorie or cal, is really a kilocalorie. In relation, some of the various heat units are ito. So take note of this equation. This is our constant. 1 calorie is equal to 3.968 times 10 raised to negative 3 BTU, or that is equal to 4.1868 joules. Okay, this is the equivalent value in terms of BTU and in terms of joules. Yeah. Next, we have the absorption of heat by solids and liquids. So first we have the heat capacity, or simply C. So ano yung heat capacity? So again, it will depends no on substances natin or elemental solids natin. Okay? So the heat capacity C of an object is the proportionality constant between the heat Q and that the object absorbs or losses and the resulting temperature change delta T of the object. So that is heat now is equal to the heat capacity multiplied the change in temperature, or that is equal to C times the final temperature minus the initial temperature. Okay, so of course this is in respect with the object. Okay, so heat capacity has the unit of energy per degree or energy per Kelvin. So the heat capacity of, say, a marble slab used in a bun warmer might be 179 calorie per degree Celsius, which we can also write as 179 calorie per Kelvin, or just as 749 joules per Kelvin. So the word capacity in this context is really misleading in that it suggests analogy to the capacity of a bucket to hold water. Okay, so the analogy is false, and you should not think of the object as containing heat or being limited in its ability to absorb heat. So heat transfer can proceed without limit as long as the necessary temperature differences is maintained, and the object may, of course, melt or vaporize during the process. So it depends sa capacity, sa heat capacity natin. Then next, we have the specific heat. Okay, so two objects made of the same material, say marble, will have heat capacities proportional to their masses. So with respect to their mass. So it is therefore convenient to define a heat capacity per unit mass, or specific heat that refers not to an object but to a unit mass of material of which the object is made. So we have here the equation 14 from equation 13 dito, or that is the heat now is equal to the specific heat multiplied by the mass multiplied by the change in temperature. Okay, so through experiment, we would find that although the heat capacity of a particular marble slab might be 179 or 749 joules per Kelvin, the specific heat of marble itself in the slab or in any other marble object is 0.21 calorie per gram times degrees Celsius, or that is 880 joules per kilogram Kelvin. So from that way, the calorie and the British thermal unit were initially defined the specific heat of water, which is 1 calorie per gram degree Celsius is equal to 1 BTU per pound degree Fahrenheit, or that is equal to 4,186.8 joules per kilogram Kelvin na dayon. Okay, so muna siya itong nga equation. So we have here the table, ito, table 3. So these are some specific heats of molar specific heats no, at room temperature. So take note at room temperature. So ano yung room temperature natin? You can recall, in degrees Celsius, what is the room temperature? Ano yung room temperature natin? Normal room temperature. Still, can still recall? Ano yung normal room temperature natin? Wala. So that will be your assignment also. Okay, so table 3. Okay, so yun na yun. No? We have the molar specific heat. So ano yung tinatawag nating molar specific heat? So in many instances, the most convenient unit for specifying the amount of substance is the mole. Diba? So 1 mole is equal to 6.02 times 10 raised to 23 units of any substance. So thus, 1 mole of aluminum means that is 6.02 times 10 raised to 23 atoms. The atom is the elementary unit, no? And 1 mole of aluminum oxide means 6.02 times 10 raised to 23 molecules. So that is the molecule. The molecule is the elementary unit of the compound. So then they're what we call molar specific heats. So yun din yun. Ito rin yun. So we have specific heat. Then we have the molar specific heat. Yan. So this is only for elemental solids, no? Ang sa molar specific heat. Other solids, wala tayo dyan. And liquids, wala rin. So next we have heat of transformation. So heat of transformation, when energy is absorbed by heat by a solid or liquid. So what will happen to the temperature? The temperature of a sample does not necessarily rise. Instead, the sample may change from one phase or state to another. So matter can exist in three common states, diba? In solid, in liquid, and in gas or vapor state. So to melt a solid means to change it from solid state to liquid state. So we need to vaporize naman a liquid means to change it from liquid state to vapor or gas. So ano pa? Condensing. Yan. So condensing a gas to form a liquid is a reverse of vaporizing. So it requires that the energy must be removed from the gas so that the molecules can cluster instead of flying away from one another. Diba may question ko before sa inyo? Nga man ang baso nga may tubig, tap water, kung butangan mo sang ice, nagapamalhas. Do you remember that one? Sa inyo kung napamangkot or sa ibang year? Sa iba sigurong year. Nga man ang baso na may tubig, umutangan sang ice, nagapamalhas. So try to check that one. What causes the sweat of the a glass of water? Then we have the heat of transformation. Yeah, so this is just the heat of transformation times the mass. Yan. Okay. So given naman yung mga formula natin dito. And some constants here. So you will use this one sa inyong exercises. Okay, so heat of vaporization. Ayan, so take note na lang for the standard ito constant value. Then for the heat of fusion naman, we have this one. Ayan. Anong pinagkaiba ng heat of vaporization at heat of fusion? Ito yung pag-absorb, no? Pag-absorb ng heat or from liquid to solid. Ayan. Ito, sample problem natin. So a copper slug whose mass m sub c is 75 grams is heated in the laboratory oven to a temperature T of 312 degrees Celsius. So the slug is then dropped. Ano yung slug? Parang isang copper slug na parang bar siya siguro, gamay. Slug. So a slug is then dropped into a glass beaker containing a mass of 220 grams of water. The heat capacity of the beaker is 45 calorie per Kelvin. The initial temperature T sub I of the water and then the beaker is 12 degrees Celsius. So assuming that the slug, beaker, and water are an isolated system. Isolated system meaning naka-isolate sila sa isa ka lugar. Okay? Then the water does not vaporize. So para nasa vacuum sila. So the water does not vaporize. So find the final temperature or T sub F of the system at thermal equilibrium. So in this case, you need to equalize the temperature of the systems, which is the copper slug, and then the water, and then syempre yung mga beaker. So you have here calculations natin. So because the system is isolated, the system's total energy cannot change and only internal transfer of thermal energy can occur. And because nothing in the system undergoes a phase change, wala kita sang water vapor, so the thermal energy transfers can only change the temperature. So meaning i-equate mo lang ang tatlo ka system, which is the water, the beaker, and the copper slug. Okay? So because the total energy of a system cannot change, the sum of these three energy transfers is zero. So dapat zero siya. Okay? So substitute natin yung equations 19, 20, and 21 dito sa equation 22. So we have here now the equation 23, which yields from 19 to 21, equation 19 to 21 into 22. Then manipulate natin yung formula. We can get the final temperature. Ito. So ano lang, manipulate lang ng konti yung formula. So the temperatures are contained in equation 23 only as difference. Okay, so this will be now, ito na yung formula natin. Then, input natin yung given. So you have here your mass ng copper slug, temperature, then mass ng water, then heat capacity ng beaker, yan, and so on. So salpak lang dito sa formula. Then you will have approximately 20 degrees Celsius yung answer mo. And so from the given data, you can show that the heat of water is equal to 1,670 calorie. For the beaker, nearly 342 calorie. For the copper naman, that is negative 2,020 calorie. So meaning, nag-dissipate yung heat niya dito. So negative yung heat capacity. Negative heat natin dito. Dito naman is positive. Positive yung water tsaka yung beaker. Sa copper, negative tayo. Yan. So apart from the rounding errors, the algebraic sum of these three transfers is indeed zero. So sino yung nag-absorb? Sino yung nag-release ng heat? So si copper yung nag-release. Nag-absorb si water tsaka si beaker. Yan. In that case, we can conclude that their temperatures are not equilibrium. I-sum up mo lang siya sa zero. Yan. Tulad ito. Isolated mo siya eh. Isolated siya. Then wala sasang changes. Phase change. Walang water vapor. And so on. Yan. Then we have here another sample problem. So how much heat must be absorbed by the ice of mass equal to 720 grams at negative 10 degrees Celsius to take it to the liquid state at 15 degrees Celsius. So I think may mga example na tayo dito before sa introduction sa physics. No? So try to review that one. Okay. So ano yung process natin dito? So first step, the ice cannot melt at a temperature below the freezing point. Initially, any energy transfer to the ice heat can only increase the temperature of the ice until 0 degrees Celsius is raised. So the temperature then cannot increase until all the ice melts. So any energy transfer to the ice as heat now can only change ice to liquid water until all ice melts. Tama. And now, the energy transferred to the liquid as heat can only increase the temperature of the liquid water. So first, we need to warm the ice. So the heat Q sub 1 needed to increase the temperature of the ice from the initial value of negative 10 degrees Celsius to a final value of 0 degrees Celsius. Para ma-melt natin siya, dapat hindi siya below the freezing point. Diba? Kaya freezing point natin is 0 degrees Celsius. Boiling point naman is 100. Diba? So that is given by the equation 14. This Q is equals to Cm delta T. So using the specific heat of ice in table 3, previous pages, we can have the heat needed to increase the temperature, that is 15.98 kilojoules. So this is for warming the ice. How about melting the ice? So now, for the melting naman, so you need to melt all the ice, which is given in equation 16. That is, the heat is equals to the L, or the heat of fusion, times the mass. Okay? So given man gyapon naton nga mass, di ba? So we have for 720 grams, or that is 0.72 kilograms. Para ma-cancel out ang atong kilogram here. So that is 239.8 kilojoules. So this is now the heat of fusion, or the heat that is needed to melt the ice. But the problem here is how much heat must be absorbed by the ice to take it to the liquid state at 15 degrees Celsius. So we need to warm the liquid. Okay, so the heat here needed to increase the temperature of the water from the initial value. So you have 0 degrees Celsius to the final value, which is up to 15 degrees Celsius. Ito yung given the final temperature with a specific heat of liquid water. So that is 4,186 J. So this is constant, multiplied by 0.72 kilogram times the change in temperature. That is 15 degrees minus 0 degrees. Delta dito. Okay? So that is equal to 45.22 kilojoules. So ito na yung heat para ma-warm natin yung liquid. So the total required heat is the sum of amounts required in the 3 steps. So that is Q sub 1 plus Q sub 2 plus Q sub 3, or that is equal to 300 kilojoules. So note that the heat required to melt the ice is much greater than the heat required to raise the temperature of either the ice or the liquid water. Yan. So ito na yun. Answer natin. Okay. So let's have a 5-minute break muna. Ganun ba dito before we go to the next section, masulod na ko sa office. May ikuha na ko. Have a 5 minutes break. Stop share muna. So we will back at 4:18. Okay, 4:18, back tayo 4:18. Okay. Ayan. So, sorry. Ayan. Okay, sige. So, again, no, let us take our system a gas confined. Ayan. So, a cylinder with a movable piston. So, parang nasa ano siya, nasa gas chamber. And so, the walls of the cylinder, ito. So, this is insulated. Insulated yung lead shot natin and yung thermal reservoir natin dito. Okay, so the bottom of the cylinder rests on a reservoir for thermal energy, and a thermal reservoir, or perhaps a hot plate, whose temperature T you can control by turning a knob dito. Yan. So, ito yung example nito siguro is ano, yung sa engine mismo, no, sa piston engine mismo ng sasakyan. Okay, so the system or the gas starts from an initial state I. So described by a pressure P sub I and a volume that is V sub I and a temperature that is T sub I. So you want to change the system to a final state F. So described by a pressure PF or P sub F, a volume V sub F, and a temperature T sub F. Okay? So yung subscript natin, pag I, initial yan. Pag F, final. Okay? So the procedure by which we change the system from its initial state to its final state is what we call thermodynamic process. Take note. So this is the process in which we call thermodynamic process. So from its initial state to its final state. That is thermodynamic process. So during such a process, so energy may be transferred into the system from the thermal reservoir dito into the system from the thermal reservoir positive heat, okay, or vice versa, that's negative heat. Okay, so energy natin may be transferred into the system from the thermal reservoir or vice versa. So this also could work, no, in a system or by the system to raise the loaded piston or what we call the positive work na. Or pwede siya ibaba, what we call the negative work. So we assume that all such changes occur slowly with the result that the system is always in approximate thermal equilibrium. So that is, every part of the system is always in thermal equilibrium with every other part. Okay, so the same temperature of both systems. So suppose that you remove a few lead shot dito. Ito yung mga lead shot mo sa loob. So suppose, no, you remove a few lead shot from the piston of figure above. So allowing the gas to push the piston and remaining shot upward through a differential displacement, or that is ds, with an upward force F. Meron tayong subscript na arrow dito, or that is vector arrow. So since the displacement is tiny, so we can assume that it is constant during displacement. Hindi mo siya ma-measure actually. So we can assume that it is constant. Then the upward force has a magnitude that is equal to the pressure times the area. Okay? So this is now the differential work is done by the gas during the displacement. So the differential work is equal to the upward force multiplied by the displacement or the differential displacement, or that is equal to the pressure times the surface area of the piston multiplied by the differential displacement, or what we call the ds. Yan. Or work now is just equal to pressure times the differential volume. Okay? So differential work is just equal to, pwede siya maging upward force multiplied by the differential displacement, or pwede siya maging equal to pressure times the differential change in volume. Okay, so this is a change in the volume of the gas due to the movement of the piston. Yeah, so when you remove, or when you have removed enough shaft to allow the gas to change its volume from initial volume to the final volume, then the total work done by the gas is equal to the integral of work equal to the pressure multiplied by the differential of the volume, or differential change in the volume from initial volume to the final volume. So we have the lower limits and the upper limits. Okay, so since wala pa kita ka-start sa atong integral calculus, you can explore this one, this formula. Okay, so this is the integral differential formula now for the work. So during the volume change, the pressure and temperature may also change. So to evaluate this equation, we would need to know how pressure varies with the volume for the actual process by which the system changes from state I to state F, or from initial state to final state. So ito yun. Ito yung process natin. So the shaded area here represents the work done by the system as it goes from initial state to final state. From initial state to final state. So work here is positive because the system volumes increases. Okay. So work is still positive dito, but now greater. Okay. And we still positive, and we are still positive here. Pagdating dito. Pero smaller na siya yung volume natin. O yung pressure natin, mababa na, smaller yung pressure natin. Okay. Ito somewhat the same. Okay. So it still goes from I to F, but now it does less work because the pressure is smaller. Then pagdating dito, we can even the work here can even smaller, no? From initial to final. So we can control how much work it does. And here, the system goes from state final, so final state siya, pabalik to initial state as the gas compressed to less volume. So moving from F to I, so therefore it does negative work. And for here, the net work done by the system during a complete cycle is represented by the shaded area dito. So cycling clockwise yields a positive network dito. Okay, but the network here is greater than 0 pa rin. So there are actually many ways to take the gas from initial state to final state. So one way is shown in figure A. Ito yung one way niya, which is the plot of the pressure of the gas versus its volume, which is called the PV diagram, pressure volume diagram. And same lang din. Okay. So a system can be taken from a given initial state to a given final state by an infinite number of processes. So heat may or may not be involved, and in general, the work and the heat will have different values for different processes. So we say that heat and work are path-dependent quantities. So it depends, di ba? So path-dependent quantities yung heat natin dito and work. Okay, so sa figure A naman, dun sa last part, example niya is negative, no? Negative work is done by the system or is done by a system as an external force compressed system reducing its volume. So meaning the gas is compressed and therefore the work done by the gas is negative. Then for the F naman sa last na figure, so it shows the thermodynamic cycle. Yan. So may cycle siya. So some of the positive work during the expansion and then negative work naman during the compression. Okay, so cycle lang. Positive, negative, positive, negative. So pag nag-expand siya, positive. Pag nag-compress siya, negative. Yan. Okay, so we are now halfway to our module 1. So we are now in the first law of thermodynamics. So we are done with the heat, no? Pressures, volumes. So the first law of thermodynamics, so you have just seen, no, what that when a system changes from an initial state to final state, so both the work W and the heat Q depend on the nature of the process. So experimentally, however, we find a surprising thing, no, that the quantity QW is the same for all processes, but it depends only on the initial and final states and does not depend on all how the system gets from one to the other. So all of the combinations of Q and W, including the Q alone or the heat alone or the work alone, or the heat and the work, and the heat minus the twice the work are path dependent. So only the quantity that is heat minus work is not, or the quantity Q minus W must represent a change in some intrinsic property of the system. So this is what we call the property of internal energy, or E sub int, and we write it as the change in internal energy equal to the internal energy multiplied by final internal energy minus the initial internal energy, or that is equal to the heat minus the work. So this is the first law of thermodynamics. If the thermodynamic system undergoes only differential change, then we can write the first law as the differential of internal energy equal to the differential of heat minus the differential of work. So the internal energy of a system tends to increase only if energy is added as heat, and tends to decrease naman if energy is lost as work done by the system. So the first law of thermodynamics is an extension of the principles to systems that are not isolated. Okay, so take note, this only works to the principles of systems that are not isolated. So in such cases, energy may be transferred into or out of the system as either work or heat. In our statement of the first law of thermodynamics, we assume that there are no changes in kinetic energy or the potential energy of the system as a whole. That is the change in K equal to the change in U, or which is equal to 0. So before this, the term work and the W always meant the work done on a system. However, starting with equation 24 and continuing to the next topics about thermodynamics, we focus on the work done by a system or by the system. Okay, work done by a system, such as the gas in previous figures. So the work done on a system is always the negative of work done by the system. So if we rewrite the equation 26, this one, the first law of thermodynamics, in terms of the work done on the system, we have the change in internal energy equal to the heat plus the work on the system, in the work by the system. Okay, so this tells us the following, which is the internal energy of a system tends to increase if heat is absorbed by the system. Okay, or if positive work is done on the system. Conversely, the internal energy naman natin tends to decrease if heat is lost by the system or if negative work is done on the system. Kasi maglasa bala ka mo sa by pag sa on. Okay. So we have here some special cases of the first law of thermodynamics. So we have 4. So what are these? So first we have the adiabatic, adiabatic processes. So in this process, one that occurs so rapidly or occurs in a system that is so well insulated that no transfer of energy as heat occurs between the system and its environment. So here we put heat is equal to 0 in the first law of our equation. Okay. Therefore, we have the change in internal energy that is equal to the negative work. So this tells us that if the work is done by the system, that is, if work is positive, the internal energy of the system decreases with the amount of work. Conversely, if work naman is done on the system, that is, if work is negative. Therefore, the internal energy of the system increases by that amount. So in this figure, no, so dito nagsimula, or it shows, no, an ideal adiabatic process. So heat cannot enter or leave the system because of the insulation. Okay, may insulation tayo dito. Thus, the only way to the energy can be transferred between the system and its environment is by work, which is up, down, like a piston. So if you remove the shot from the piston and allow the gas to expand, so the work done by the system or the gas is positive. And then the internal energy naman natin of the gas decreases. If instead we add shot and compress the gas, the work done by the system is negative and the internal energy of the gas increases. Yan. So next we have the constant volume process. So that is for the adiabatic processes. So next we have the constant volume processes. So the volume of the system, such as gas, is held constant. So that system can do no work. Putting work is equal to 0. Then our first law equation now is equal to the heat, or that is the change in internal energy is equal to heat. And that is if Q is positive. Okay, so meaning heat is absorbed by the system. So the internal energy of the system increases. Conversely, if heat is lost during the process, so that is if Q is negative, the internal energy of the system must decrease. Okay. So here we have the ito yung table 5 natin for the first law of thermodynamics. Ito yung restrictions and consequences. Ito yung processes. So ito yung sa adiabatic, constant volume. And the third one is the closed cycle. And the last is the free expansion. So dito naman, sa cyclic process, yung heat natin is equal to work. Yan. So the net work done during the process must exactly equal to the net amount of energy transferred as heat. So the store of internal energy of the system remains unchanged. So therefore, equal lang yung heat natin at work. So cyclical process form a closed loop on a PV plot or pressure volume plot natin, shown in figure F. Dito sa taas kayo na kanina. And the last one is the free expansion, wherein yung internal energy natin is 0. Okay. Thus, yung heat and work natin is 0. Okay, so these are adiabatic processes in which no transfer of heat occurs between the system and its environment, and no work is done on or by the system. So 0 lang siya. And next, okay, we have here a sample problem. So let's say we have 1 kilogram of liquid water at 100 degrees Celsius. Be converted to steam at 100 degrees Celsius by boiling at standard atmospheric pressure, which is 1 atm, or that is 1.01 times 10 raised to 5 Pascal. In the arrangement of the figure below, the volume of the water changes from initial value of 1 times 10 raised to negative 3 cubic meter as a liquid to 1.671 cubic meter as steam. Okay, so let's say meron tayong parang generator gamit ng steam. Okay, so the question here is how much work is done by the system during this process. So the system must do positive work because the volume increases. Okay, yan yung hint nyo. Diba? So kung titingnan nyo yung change ng volume natin dito, nag-increase siya. Okay, so meaning, when the volume increases, the system must do positive work. Dapat yung work mo dito is positive. So we calculate then the work done by integrating the pressure with respect to the volume. So the given volume here is volume of the water. So initial value of 1 times 10 raised to negative 3. And compared to the atmospheric pressure. Okay. So because here the pressure is constant, so may constant tayong pressure that is 1.01 times 10 raised to 5 Pascal. So we can take P outside the integral. Ito yung constant natin dito. So ilabas natin siya yung constant. So later on, we will discuss na sa calculus 2 natin yung first formula for integral. Okay, so this is part na of integral calculus. Okay, so try to analyze this one. Then once you come up with the formula, just salpak-salpak na lang the given. Okay, salpak na natin yung given. You have your change in final volume and initial. You have 1.671 cubic meter minus the 1 times 10 raised to negative 3 cubic meter. And so given naman siya, ito yung value mo, initial, then papunta dito. Steam. Yan. So nag-change yung water. Volume of water changes from initial value as liquid and then nag-changes into steam. So water pa rin siya, pero yung volume niya nag-change. Okay. So ito na yung answer mo. Ito yung work. This is the work done by the system during the process. Next question is how much energy is transferred as heat during the process. So because the heat causes only a phase change and does not change in temperature. So take note nga yung temperature natin is just the same, di ba? So ano lang, the same yung gihapon, 100 degrees Celsius. Ayan, converted to steam at 100 degrees Celsius by boiling. Therefore, yun. So yung phase change natin is from liquid to gaseous phase. So L here is the heat of evaporation. And LV, the volume given. Okay, so that is the heat of vaporization times the mass. So given naman yung heat of vaporization natin, that is 2,000, given ba? Wala. Hindi given, no? This is constant, no? Heat of vaporization. So this is sa table 4. Dito. Table 4. Constant siya. So take note of the tables natin dito sa notes natin. Ayan. Ito. Heat of vaporization. Water, we have 2256. Boiling point is 373. Okay. So, yun. 2256 kilojoules per kilogram multiplied by 1 kilogram. Yung 1 kilogram dito is given, I think. Ito siya. Water. Then, therefore, yung energy natin as heat is nearly equal to 2,260 joules. So, ito yung energy na na-transfer as heat during the process. And Then for the next question, what is the change in the system's initial internal energy during the process? So for this one, we write the first law as change in internal energy. That is equal to the heat minus the work. So given naman yung heat, di ba? Ito yung heat natin. That is 2,260. Ito pala yung ano, yung heat pala na, ito kasi ano to eh, energy transferred as heat. Then dito, yung heat natin dito is yung talagang constant heat ng water. That is 2256 kilojoules. Minus the work done is 169 kilojoules. So ito siya, yung work done by the system during the process, 169 kilojoules. So therefore, yung internal energy mo is nearly equal to 2090 kilojoules, or that is 2.09 megajoules. And so this quantity is positive, meaning the internal energy of the system is increased during the boiling process. So this energy goes into separating the H2O molecules, or the water molecules, which strongly attract one another in the liquid state. So therefore, we see that when water is boiled, about 7.5% of the heat goes into the work of pushing back to the atmosphere. Then the rest of the heat goes into the system's internal energy. Yan. Ito yung interpretation ng data natin. So next, we have the heat transfer mechanism. So paano ba mag-transfer yung heat from cold to hot ba? From hot to cold? Any idea kung paano nag-transfer yung heat? Saan ba yung mas madali? Yung nagtimpla ka ng kape tapos naglamig siya? Or nag-create ka ng or gumawa ka ng yellow, gumawa ka ng ice from tap water. So saan banda? Heat to cold, or hot to cold, or cold to hot? So first, we have three transfer mechanisms. We have the conduction, convection, and radiation. So this was already discussed during our physics 1. Okay, so conduction, meaning if you leave the end of a metal pulper in a fire for enough time, its handle will get hot. So energy is transferred from fire to the handle by thermal conduction along the length of the pulper. So the vibration amplitudes of the atoms and electrons of the metal, the fire end of the pulper, become relatively large because of the high temperature. So no need to discuss this one. I think you just need to review this one. The conduction, convection, and radiation. Ayan. Then we have some thermal conductivities. Okay. So alam naman natin, no, that it will depends, no, sa thermal resistance. Of course, the length sang ating or thickness sa ating metal. Diba? Then you can analyze if it is a poor thermal conductor or good thermal insulator. So just try to read this one. Then convection naman. Okay, so when you look at the flame, so convection, no? So ayan. So such energy transfer occurs when fluid, such as air or water, comes in contact with an object whose temperature is higher than that of the liquid. Okay, so the temperature of that part of the liquid that is in contact with a hot object. So, and in most cases, the fluid expands and become less dense. So because this expanded fluid is now lighter than the surrounded cooler fluid, so we have the buoyant forces, which causes it to rise. Yeah, so convection is part of many natural processes. So we have atmospheric convection, which plays a fundamental role in determining global climate patterns in daily weather variation. So glider pilots naman and birds alike seek rising thermals. So convection currents of warm air that keep them aloft. And huge energy transfers takes place with the ocean by the same process. So yan yung sa convection. Radiation naman, so this is the third method, no? So exchange of energy, okay? So which an object and its environment can exchange energy as heat is via electromagnetic waves. So via electromagnetic waves, so this visible light is one kind of electromagnetic wave. So the energy transferred in this way is often called thermal radiation. Distinguish it from electromagnetic signals sa mga TV natin, sa TV broadcast, and from nuclear radiation. So this is energy and particles emitted by nuclei. So to radiate generally means to emit. So when you stand in front of a big fire, you are warmed by absorbing thermal radiation, of course, from the fire. So that is your thermal energy increases as the fire's thermal energy decreases. So no medium is required for heat transfer via radiation. The radiation can travel through vacuum from, say, let's say, sun pakadto sa atom. What we call the sun radiation. Okay, so we have here the formula. So the rate P rad, P sub rad, at which an object emits energy via electromagnetic radiation depends on the object surface area. Okay, and the temperature of that area in kelvins and is given by this equation. So yung rho natin dito is equal to 5.6704 times 10 raised to negative 8 watts per meter squared Kelvin raised to 4. So ito yung tinatawag nating Boltzmann constant. Boltzmann constant. Okay, so this is constant. Para ni siya sa inyo calculator. Boltzmann constant. Okay, then multiply na natin by this epsilon. Ano yung epsilon dito? Forgot. Ito. It represents the emissivity. Okay. Represents the emissivity of the object surface. So this has a value between 0 and 1. Okay, may value siya from 0 to 1. So of course, depende sa composition of the surface. So a surface with a maximum emissivity of 1 is said to be a black body radiator, but such a surface is an ideal limit and does not occur in nature. So wala siya. It does not occur in nature. Okay, then we have absolute. Okay. At which object absorbs energy via thermal radiation from its environment, no? So which we take to be at uniform temperature, which is in kelvins ng gihapon. So the same equation, Boltzmann constant times the emissivity times the area times the temperature raised to 4. Okay. So dito, an idealized black body radiator with emissivity is equals to 1 will absorb all radiated energy it intercepts. Rather than sending a portion back away from itself through reflection or scattering, i-absorb niya siya. Okay, i-absorb niya. And because an object will radiate energy to the environment, well, it absorbs energy from the environment. The object's net rate, the P net of energy exchange due to thermal radiation is ito, this equation. So that is the P sub net is equals to P sub absolute minus the P sub rad, which is equal also to the Boltzmann constant times the emissivity times the area, of course, multiplied by the change in temperature. Okay, so temperature in terms of the environment is the temperature of the system mismo. Ayan. So kung yung energy natin, net of energy natin is positive, then meaning it is being absorbed via radiation. But if it is negative, then meaning it is being lost via radiation. Okay. So we have your sample problem. So figure shows the cross section of a wall Okay? So parang meron siyang firewall made of white pine of thickness L sub A and a brick thickness of L sub D, which is a diameter of parang 2 sub LA. O twice the thickness of the white pine. So sandwiching two layers of unknown material with identical thickness and thermal conductivities. Okay. So the energy transfer per second is the same in each layer. So here the steady state heat transfer through a wall. So the thermal conductivity of pine is, let's say we have T sub A, and that of the brick is K sub D. Ito yung sa pine, ito yung sa brick. Ito yung dalawang material na unknown. Okay, this is the two layers of unknown material. Okay, so the face area of the wall is unknown also. Wala tayong alam. Then the thermal conductivity through the wall has reached steady state. So meaning the only known interface temperatures are T sub 1, which is 25 degrees Celsius. This is the room temperature. T sub 2, 20 degrees Celsius. And T sub 5, which is the negative 10 degrees Celsius. So what is interface temperature T sub 4? Yun yung question. So temperature T sub 4 helps determine the rate P D at which energy is conducted through the brick as given equation 32. However, wala kita sa data. Wala nga atong given. Okay, so because of the conduction is steady, therefore the conduction rate P sub T through the brick must be equal to the conduction rate P sub A through the pine, which gets us going to this equation. Okay, so meaning with the use of, because of the conduction is steady, we use the conduction rate PD through the brick, which is equal to the conduction rate of the pine. Okay, in-equate na natin. So meaning PA is equals to P sub A is equals to P sub D. And solving for the T4 here, so manipulate na natin yung formula para ma-eliminate yung known and then transpose natin yung unknown, which is the T sub 4. Okay, so letting LD, so again, salpak na natin yung given na parameters, so that is 2 times LA or L sub A. Then we have the KD, that is 5 times the KA, and inserting the unknown temperatures, that is for T sub 1, T sub 2, and T sub 5. And therefore, cancel out yung LA dito and yung KA dito. So you can find that the temperature here is negative 8 degrees Celsius. So therefore, this is your temperature at this interface, T sub 4. Okay. So meaning, when you see an illustration like this, so yung T5 niya is negative 10. So meaning, hindi siya dapat lalagpas ng negative 10 dito. Okay. Mas higher siya dapat sa negative 10, which is negative 8. So tama lang. Diba? Okay, so that's it for our module 1. So questions, clarifications. Okay, so by the way, ang atong references aron naman sa NEO LMS, you can check that one. So learning materials, I think upload ko siya sa what you call that one? Sa Google Drive, ang atong PDF, no? So for the next module, we will, I think na-upload ko ang next module natin. So na-upload ba? Ayan. So we will study the thermodynamics, no? The same ang gihapon, thermodynamics, but heat engines na. Okay, so we will discuss the heat engines, entropy, and the second law of thermodynamics. Next week. Next Monday. And wait, I'll stop sharing.